Guys, is my screen visible?
Yes, we can see it.
Okay. This is visible, right? Once again.
Yes.
Okay, fine. So, sorry for the delay. There was some connectivity issue. Okay, so now we reach to the end of summer school. So in these sessions, we discussed a lot. Like in the initial part, we discussed about designing CAD and dynamics of the model and dynamics of the robot, and then we saw electronic circuitries, and then we saw control systems and their implementations. So all these were focused on the hardware part. Now, in the later sessions, we saw about ROS and its utilities, and also CVI. So all those ROS and CVI, most those things we'll be using for automation of the robot. So this is the phase where we'll be automating the robot. Okay. So basically, we want the robot to move on a command without actually controlling it. So that's why we use all these algorithms and we plan a path accordingly. Okay. So let's say our bot wants to move from point A to point B. So what all things it's required? Firstly, it requires some proper map and its proper location. And second thing, it needs a proper path to propagate, right? So this SLAM part will be dealing with creating a proper map and locating the robot locally in that map. And in the next part, path planning part, we'll be discussing about planning a shortest path with minimal cost, and then we will be implementing this automation. Okay. So yeah, so let's begin with SLAM. SLAM is nothing but simultaneous localization and mapping. So it's a fundamental concept in robotics where we use sensor data and all the other datas, and we will track, we will formulate the map and we'll track our robot's position according to that map. Okay. So now here we are seeing two things: localization and mapping. So in this part, we will be discuss what is localization, what is mapping, and how are those two integrated, and how are those two integrated simultaneously. We will see. Okay. So first, SLAM. We saw what is SLAM. We got a basic idea of what is SLAM. So first, we need to see what is localization. So localization is refers to a process of estimating the pose. Pose is nothing but position and the orientation of the robot or the system within the environment. Now let's say the robot is in a surrounding environment. So we need to know like where the robot has been positioned, right? That might be either coordinate with respect to a coordinate axis or with respect to features or something. Now imagine you are in a mall and your friend wants to visit you. So the thing is, if you want to send the location of your if you want to send your location to your friend, what you would be saying, you'll be saying get inside the first entrance, there will be a lift over there, and go to second floor, and in the right hand side there'll be KFC, like that. You will be giving some set of regulations, some set of instructions, right? So those things are also some sort of is I mean some sort of estimating the position of estimating your position. So we generally call those things as features. Okay. So in this part we will just we will see how to map the robot according to the features, and how are we exactly doing this localization. So this is basically localization. Okay. Now, mapping involves constructing a representation of the surrounding, such as location of obstacles, landmarks, and other features. Like I said, we need to have a proper map in order to do the in order to automate the robot, right?
Yogesh,
Yes.
I think your screen is stuck.
Oh, in which page it is in?
It's only showing the Teams page.
Oh, just a second. Yeah, can you see the screen now, or can you only see the teams?
Yeah, I can still see the teams.
Okay, just a second. Hello, am I audible?
Yes.
Yeah, can you confirm us what you can see?
Yeah, I think it's working. I can see the thumbs up and all.
No, no. Can you able to see the PPT?
Right now, no. Okay, so Yogesh is currently fixing his issues. So until then, I'll continue the successing part. Okay, so can you screen? Can you see my screen? Yeah, okay. Okay, so let us start with path planning algorithm. So the previous step of path planning algorithm is localization and mapping. So basically, I'll just give a brief about SLAM and SLAM. Okay, so what happens is in SLAM is that we uh, make a map of our environment using the sensor data, the sensors which are attached to our robot, and then using that we create a map. So after we have the map of the environment, then we somehow need to uh, get, I mean, we have to find our way through the map, right? So for that, we use path planning algorithms. So because path planning algorithms are a bit complex in implementation, so I am only going to just give a brief about them. Just I'm going to show you how they work and all their mechanism. The code and implementation part for now I'll be skipping. So although I've attached some resources in the end, you can see them if you like. So for now we'll only focus on the basics. Okay, so yeah, after localization and mapping, we need to find a way through the environment, right? Just like a maze solving robot finds its way through the maze uh, up till its final destination. Also, we have the service robot, which can attend to different people's needs by following the corridors of the hotel and all. So how do they all manage to do this? So basically they have a map of their environment, and then we use the path planning algorithms to just find the path from their current position to their destination. So before we move on to the path planning or algorithm specifically, we are going to look at graphs. Okay, so graphs are a data structure which we are going to use throughout the whole lecture actually. So all the methods we are going to learn today are based on graphs. And so graph is a data structure, but for this lecture, just remember that graph is something like this. It consists of these circles which are called nodes, and then the edge that connects the nodes. Okay, yeah, the nodes are connected by an edge. So and it just forms this kind of structure by linking different nodes with each other. So for this lecture, just remember this is how a graph looks like. Okay, so how are we going to use the graph in this lecture? Okay, yeah, so we are mainly going to use the graph in two ways. One is we are going to generate a tree structure using these graphs, and what this tree does is it travels throughout the map exploring different places from our starting location, so that we can just suppose A is our starting location. So if we use a tree, then we can explore different part of the map. Suppose we have to reach S, so we can just follow this path and we can reach our goal. So that's how we are going to use trees for our benefit. And we are going to discuss more about the methods of using trees later. Okay. So the next way in which we are going to use graph is graphs can help us basically simplify what do you call simplify the structure of a map. So suppose this is a map, okay. Now this map, while computing its the shortest path from any one point to any other point, suppose, it can be a bit tedious. So to simplify this process, we just represent this map as a graph. Okay, so this curve can be represented by straight line, and then the total distance we cover from going from this point to this point can be represented by straight line, and we can give some value to it. That is the distance, how much distance we travel between this edge. We can just give a value over here. Okay, similarly for all these parts, suppose this is a long curve, so it can be just simplified into straight lines. So it makes our work pretty easier. Okay, even in this case, there is this curved road which can be represented in a straight line. Okay, so now what are weighted graphs? So weighted graphs are basically graphs whose edges have some values. The value can be like distance. Suppose in this case, the total distance going from this point right here to this point right here, sorry, to this point right here, this point to this point, we can assign some value. Like suppose it is a distance, then this edge will have a certain value. So that value is known as weight, and a graph having that value is called a weighted graph. So we are going to use these weighted graphs in search-based algorithms, which we are going to discuss later. So just keep these basic things in mind and just let's move forward. Okay, so the path planning algorithms we are going to use are broadly divided into, two groups. So one is search-based algorithm and one is sampling-based algorithm. So the search-based algorithm uses an already existing graph, uh, or a graph in which the structure is set up in an orderly manner, uh, like like in this case. Okay, the graph is generated after seeing this map, so it's an already existing map or an ordered map. Okay, and the algorithms we are going to use inside it are Dijkstra's algorithm and the A-star algorithm. We are mainly going to discuss about Dijkstra's algorithm. A-star algorithm just helps in planning the way a bit better by saving us a lot of computation. Okay, and the next method of path planning is sampling based algorithms. So in case of search based, we use an existing graph or an ordered graph structure. But in sampling based algorithms, we just randomly generate those different nodes of the graph. So we don't have any pre-built nodes or anything. We just spread those nodes like randomly, and then based on that, we try to predict our path. Okay, we'll see that in the later part of the lecture. So, and the main two examples of this kind of path planning are RRT and RRT star algorithm, which are rapidly exploring random trees, RRT. Okay, so yeah, let's move forward. Okay, so let us start first with search-based algorithms. Okay, so firstly we have Dijkstra's algorithm. Dijkstra's algorithm is used to calculate to find the shortest path between a starting node and every other node in a weighted graph. Okay, so suppose we have this graph. Okay, so from any starting point, let us say B is the starting point. Using Dijkstra's algorithm, we can find the shortest path to each and every other node of this graph. Okay, so to use it for path planning. Suppose this is a map of a city. Okay, this is a part A of the city, this is part B of a city, part C, part D, part E, part F. Okay, so if we start from suppose part B of the city, then using Dijkstra's algorithm, we can calculate whatever the shortest path is required to reach the other parts of the cities. Okay, so okay, let us now just solve this example. We will find the shortest path we need in order to go from A to every other node. Okay, and I'll be just demonstrating how the Dijkstra's algorithm works in this case. So now the first step is that what we'll do is we'll start at our starting node, that is the at part A, and then we'll label the distance is like how much distance we are away from each and every node. Okay, so we are starting from A, so we are already at A, so our distance from A is 0, so we'll just label it as 0. And we haven't yet visited B and we don't know how far it is, so we'll just for now set it to infinity. And similarly in the other case like D, F, E, C, we haven't visited them yet, so we don't know how far they are, so we'll just for now label them as infinity. Okay, so yeah, okay, so to keep track of things, we are going to use this table. Okay, so currently we are at the vertex A, so our distance from vertex A is 0. There is no previous node we have visited over here. And have we visited A? So yeah, we'll just write it as true for now. We have visited it, and you can see that currently the rest of the nodes, the distance is infinity currently, and we haven't yet visited it, so we just have set it as false. And currently we don't have any previous node for this, so let us move forward. Okay, so the next step is that from our starting node, we are going to just take a look at the like neighboring nodes. Okay, the nodes which are connected by this. Okay, does someone have to say something? Yeah, okay, that's fine. Yeah, okay. So what we'll do is we are starting from A, right? So the neighboring nodes are B and C, and to travel to B, we have to travel a distance of 4. So we'll just update that value to 4. And then for C, we have to travel a distance of 5. So we are just going to update the distance of C as 5. Similarly, we are just going to update it over here also. So for B, the distance is 4. For C, the distance is 5 to reach it. And the previous node is A because we are reaching the node B from A. Okay. And we are reaching the node C also from A. Okay. So we haven't yet visited B and C, so we will still keep it as false. Okay. Now, the next step is that after assigning these values, what we are going to do is we are going to choose a next vertex to move. Okay, so how are we going to do that? We are going to do that by choosing the unvisited vertex with the smallest value of distance on it. So in all of these vertexes, the smallest value the node which has the smallest value is of B, which is 4. So our next node is going to be B. Okay. So yeah, after this we can set, uh, we have visited B, so we can set it as true. Okay, we have visited B. And then next, we are going to continue the same steps which we did for A to the surrounding nodes of B. Now, the nodes which are connected by B are D, E, and C. Previously, D had a value of infinity, but now we need a distance of 9 from B to reach D, which is 9 plus 4, that is 13 from A. So we are just going to update this value of D to 13. Similarly, we are also going to update the value of E from infinity to 4 plus 7, which is 11. That is the distance needed to reach via this route. From B, we can reach E at 11 units. Now, C is also a neighboring node, but as you can see here that 4 plus 11 is 15. So from B to reach C, we need 11 units. But we can see that from A to C, the work is done only in 5, like 5 units. So there is no need to change the value of C. We'll just keep it as 5. Okay. And that's how the Dijkstra's algorithm works basically. So we just move from one node to the other throughout the graph, and then we just keep on updating the values as we reach there. So for now we are at B. Okay, we are at B. So we have updated the distances of D and E, and to reach D, the previous node is B. Okay, so we wrote that over here. For E also, the previous node is B. Okay, now again we are going to move on to our next node, that is from B. The next smallest unvisited one is C. So we are just going to move from B to C. Okay, so now we are currently at C. So yeah, we have set it as true. And now we are just going to like repeat this process for C and then just update, because okay, now just see this. Uh, Currently E has a value set as 11, which is the value it takes by reaching this route, like A, B, E. But when you are at C, you can see that you can reach it only at 3 units, which is much shorter than 11. So we are just going to update its value to 5 plus 3, that is 8. Okay, so the new value of E is updated at 8, and the previous node is C. Okay, now we are again going to like move on to our next node, which is going to be E, because because the only unvisited the connected node which has not been yet visited is E, which has a value of 8. So we are just going to move on to E, and then again similarly we are going to update the value of F, that is 8 plus 6 equal to 14, and the value of D will, okay, so 8 plus 13 is 21, which is like greater than D. So this route is shorter than this route. So D's value is still going to stay the same. Only the value of F is going to change to 14. Okay. And then the next step is again we are going to move on to the smaller vertex like 13 or 14. So we are going to move on to D, which has a value 13. So yeah. Now after reaching D, the only unvisited vertex is F. So do we need to change its value? Well, actually no, because to reach F through this route, we have 14 as our distance. But when you go from here to here, it is 13 plus 2, that's 15, which is greater than 14. So there is no need to update that. Okay, and just update this table also, like to reach F, previously E. Okay, so that's it. So yeah, this will be our final table after like traveling through the whole graph. This is our final table. the shortest distance to reach from A to every other node is given in this table right here. So to reach B, we need a distance of 4 units. To reach C, we need a distance of 5 units. To reach D, we need a distance of 13 units. To reach E, we need a distance of 8 units. And then to reach F, 14 units. Now, how do we calculate? Now we have calculated the distances. So how do we calculate the path? Like we need to find the path to F, right? So how we are going to do is the vertex you need to reach F, just move with previous. So F, E. Okay. Then we have E. What is the previous vertex of E? That is C. And then what is the previous vertex of C? That is A. And A is the starting point. So that is how we can like backtrace to just find our path. Okay. So using this table, we can just backtrace and find our path. Okay. In this case, the graph is too simple, so it is easy to even see like this. But in very complicated graphs with multiple nodes and edges, it can be difficult. So using the table, we can just retrace to find our final path, which is the shortest one. So using the data, we found out that this is the shortest path for F. For E, this is the shortest path, ACE. To reach D, ABD is the shortest path. To reach C, just AC. To reach B also, just AB. Okay. So yeah, that's pretty much how Dijkstra's algorithm works. Okay. So do you have any doubts until now? So if you have any doubts, just write it out in the chat. I'll see it after some time. Okay. So yeah, let us now move to the drawbacks of Dijkstra's. Okay, so even though Dijkstra's algorithm helps us to find the quickest route in a graph, uh, the one like major drawback is that, and we will see that through an example. Okay, so suppose we have this region right here. Okay, this is our region, and suppose we have to move from this point. This red point is our starting point, and this green point is our destination point. Okay, so if we have to move from the starting point to the ending point, we can't just like estimate this by our own. So here we use path planning algorithm. So using Dijkstra's algorithm, how we can do that is that we can just divide this whole page by nodes. Okay, so the whole region can be covered by different nodes. Okay, so this destination is also set on a node, and then there are these equally spaced node. Although I have in this picture they are not equally spaced, but just assume that they are equally spaced. Uh, okay, so we just divide the whole region into nodes. Okay, and we are going to use Dijkstra's algorithm on this graph in order to find the shortest path to reach this point over here. Okay, now Dijkstra's algorithm will find the shortest path. Okay, but the problem is that even though we found the path over here, it is still going to run throughout the whole graph and do these additional computations which are not actually needed by us. So that makes it computationally very expensive, especially if the nodes are like very small and then they are spread throughout the page. Like suppose there are like 1,000 nodes over this side, 1,000 nodes over this side. So that's almost like 1 million nodes or something. So in that case, it will be, if we want to just find the path, then it will be like computationally very expensive. You have to do a lot of computation to find the shortest path. Okay, so another uh, drawback Okay, so the similar drawback can be seen here. Suppose this is a map, okay, and we have to go from Prague to Rome. So how, and this is the graph of the structure of roads in Europe. Okay, so to reach Prague to Rome, this is supposed to be the shortest path, okay, which is found by Dijkstra's algorithm. But in order to calculate the shortest path, Dijkstra's algorithm have to visit this whole different regions all around the map, which are not actually necessary, because we aren't even reaching here. When we say our destination is on this side, but we are still exploring all these other parts which are not actually necessary. So we need a way to fix that, because Dijkstra's algorithm just moves from the starting node to the one which is nearest. Okay, so then it will just, even though the destination is over here, it will just go on this side. So we need something which can reduce that computation. So then here is where A star algorithms comes into picture. Okay, so A star algorithm is similar to Dijkstra's, but we are going to do one clever thing over here. What we are going to do is we are going to prioritize our path. Suppose in Dijkstra's, our destination is on this side, right? So instead of exploring all these areas, we are going to just start a little bit on every side, and then we are going to check if moving on that path is actually going to get us nearer to our goal or further from our goal. Okay, the path which is going to get us nearer to the road, we will prefer to like compute that path first. If we are not able to find, then we can compute the other one. So that's the main idea of that A star algorithm. So this is how it looks like after applying Dijkstra algorithm, right? So after applying A star algorithms, we don't have to like visit all these parts. We only visited this small part before like computing the shortest path. In Dijkstra's, all these paths were visited, which like led to unnecessary computation. So how do we do that using A star algorithm? So what did we implement differently? So that is what I said. In A star algorithm, we track whether we are moving towards our direction or we are moving away from our direction. Sorry, away from our destination. So we'll give preference to the nodes which reduce our distance from the destination, and we are going to compute that path first. Okay. So for that, A star uses something called this heuristic function. Okay. Uh, so let us just understand it. Suppose we are currently at this node, and then A, B, and C are its neighboring nodes. Okay. Now, if we use Dijkstra's, we'll first visit the shortest one, then the next shortest, then the next shortest, and over again. But in what we'll do in A star is that starting from this point, we are going to just move to each and every one of these. We are going to compute the value of that node. So for A, it's G1n. For B, it's G2n. For C, it's G3n. Okay. But in A star, we are also going to calculate another thing, that is Hn, which is the heuristic function. And what the heuristic function represents is that it determines whether the distance from our final goal is reduced or not. Okay, so as you can see, when we move from our starting node to C, this is the H3. Okay, so this line right here is H3n. Okay, when we move from starting to B, this is our H2n, which is a heuristic function. And then if we move to A, we get H1n. Okay, so we can clearly see that the length of we can clearly see that f for A, the what we call the value is far more greater as compared to B, and then C has the lowest value. So we will So we'll prefer to move or we'll prefer to explore the path C first, and then we are going to like explore one of these. Okay, if we don't find anything over here. Okay, so that's how the heuristic function helps us in uh, reducing our competition by a lot. Okay, and actually in most cases if we move towards our destination we can find the shortest path. Maybe in some case, suppose the path is not available over here, then it will have to check here, then it will have to check here also if it's not available here. Okay, so mostly we will be able to find our destination within C or B, something like that. Okay, and now where is A star algorithm used? So A star algorithm is used uh, now. Google Maps is one of the things that use A star algorithm to find the quickest route. Okay, so the map is divided into different nodes and sort, and it just helps us to find the quickest route. In Google Maps, what do you call uh, instead of using distance, it also uses time as one of the edges. We can use time also as our edge. Suppose one road is more crowded than the other, then the value of time will be greater for that. So that's how we can just compute which path is shorter for us, like is quicker for us, like which path we can use to reach our goal quicker. So that's what Google Map does. Also, we can use A-star algorithm to just solve these kind of maps. Okay, A-star algorithm is also used for what do you call navigating robots. Uh, One of the I think first algorithms used to like navigate robots is A-star. Okay, so yeah, let us now move towards sampling based algorithms. Okay, so in sampling based algorithm, unlike the search based algorithm, we are not going to like, arrange nodes in an orderly manner like we did previously. Like in this case, you can see we arrange the nodes in an orderly manner, and then we applied Dijkstra on this. But in sampling based algorithms, we don't do that. We generate random nodes which help us explore the whole map and reach our destination. So in some cases, A star and Dijkstra's can be more computationally heavy, but we can reduce the number of nodes by using the sampling based algorithms in some case where the space is more open. Okay, so the path planning algorithm, okay, uses graph-based method to generate random nodes. Okay, so now we are just going to understand how the random trees are formed. Okay, so again, we have this region. The path planning algorithm, okay, uses graph-based method to generate random nodes. Okay, so now we are just going to understand how the random trees are formed. Okay, so again, we have this region. Okay, there are no obstacles in between or something. It is just a basic region, and this is our starting point. This is our ending point. Okay, we need to find the path from here to here. What we are going to do in this case is that we are going to suppose set up a region around our current node, and then we are going to generate a random node, okay, within that region, which connects this node to this node, and it has some value, okay, some distance between these two. So this random node just connects our, just made a short path from this node to this node, okay. Similarly, there we can generate another random nodes surrounding this time this node, okay. So as we generate more and more random nodes, eventually, after generating so many random nodes, eventually, suppose we reach our destination. So we have found a path. Okay, this path is not the shortest or something, but at least we have found a path. Okay, so we're just going to, for now, label it as label it in red color, which indicates our path. Okay. Now, in the next step, we'll generate more nodes. Okay. Again, from we'll go to the start. We'll generate another node. Okay. And then we're going to see. Okay. Within this radius, search radius, if there is any node which can reduce the distance to a bit shorter. Okay, so in this case there is, if we connect to this node, this distance is going to be even longer, so it's not going to benefit us at all. So suppose another random node is generated over here now. Okay, now we can see that if this node connects to this node right here, then this distance is much shorter than we have to travel through all this path, but this distance is much shorter as compared to this path. Okay, so what we are going to do is we are going to update our distance. Okay, we are going to update this, update our path. So we are going to connect this node over here, and then we are going to remove this tree over here. Okay, so our new path is this. Okay, so if we just continue this process for an infinite number of time, we can finally somehow find a path which can be like called the shortest path. So if we just continue this process for infinity, then there will be some nodes which just align in a straight line, and then we can just use them to find the shortest path. Okay. Okay, so now let us do one thing. Uh, we are going to look at why just random trees, why are they not so useful when it comes to solving path planning algorithms. So for this, I'm going to just use this demonstration over here. Okay, uh, let us start it again. Hmm. Okay, so yeah, okay, so right now it is set to random trees. Okay, now let us add a few nodes over here. So as you can see, the nodes are randomly generated over here, and they form this kind of structure from the starting point, and this point is our destination. So these nodes are just going to explore the whole map. Okay, so let us add 100 more nodes. Let us add 100 more. Okay, so now you can see what is happening over here. Due to this algorithm, what is happening is that the nodes get crowded onto a single place. You can see that the nodes are just crowding onto a single place, right? Even if we add just a few more nodes, like 200 more nodes. Okay, so now we have 30, we'll have 3011 nodes or something. Okay, but we can see that it still hasn't explored the map as much. It is just crowding onto this small area right here. Okay, and our destination is still very far away from it. So let us add a few more nodes. Let us see what happens. Okay, so now we have 500 nodes, but still, I mean, we haven't reached our destination yet. Okay, so we can see that uh, they aren't very good at exploring randomly, because the thing is, what happens when we are using this is, suppose this is our search radius. What happens is that for every node generated, there is a 50% probability that the path will move towards its destination, and 50% chance that it will not move towards its destination. And even if it moves somewhere over here, the distance to the destination is still quite far. So the probability of actually exploring is far less. As I mean, so it's, we can just say that it is not very efficient in exploring the environment. Okay, let us just check uh, by adding more nodes. Okay, we have 700 nodes, but it still hasn't explored the environment much. So yeah, even if we add like more and more, let us add 500 more nodes. It will take some time. Okay, so now we have over 1,000 nodes, but I mean it's just crowding onto this. So we have to be smarter about how we generate random nodes at this point. This is what we are going to change for our, that is going to be the RRT algorithm. Okay. So what we are going to do differently in RRT algorithm is that we are going to we are still going to generate random nodes, but we are going to do it in a slightly different manner. Okay, so for this example, uh, what I've done is I haven't placed any destination point because I just want to show you how the RRT algorithm helps exploring the map. Okay, how it helps in exploring. So in this case, what happens is that instead of spawning nodes in a small area, what we are going to do is we are going to spawn a node in anywhere in this region. Okay, so we are just going to spawn a node anywhere in this region, but the node which we are going to what you call connect to this is going to be within some distance. Okay, so although this initial node is over here, we are going to connect it at a certain distance from this point. Okay, like this. So what happens is that instead of having like a 50-50 probability of exploring, it is going to have a lot more probability. So suppose, just see, if we spawn a node over here, we'll have another node here, we'll have another node like this. So now as we continue what you call spawning these nodes, and the node will just connect to the nearest other one, nearest node, like this. So you can see that even though the nodes are placed here, the nodes will rapidly connect to the ones which are a bit away from the starting node. So which will result in exploration, I mean in a much better exploration as compared to random trees. Random trees can just zigzag through like this, and just crowd the whole place. But RRT is a bit different. It just adds node away from what we call the starting point. So it just keeps on exploring more and more part of the map like this. Okay. So as compared to RR, I mean random trees, this is quite better at exploring the map. Okay, so let us now see how an RRT algorithm looks like. Okay, we'll switch to RRT. Okay. Uh, Let us try none. Okay, without any obstacle or anything. So this is our destination over here. This is our destination, and initially we have, this is our starting point, only one node. We'll add 10 nodes in the start. So we can see that how the structure, I mean we can see the structure right here, right? How it is spreading more efficiently as compared to random trees, because we can spawn nodes at any point of this map, and then because of this it has a more probability of spreading across the map. Okay, let us add suppose 10 more. Let's see. Just see how well these nodes are spreading across the whole region. Okay, let's add 100 more. Okay, okay, now in the case of random trees, after 100 nodes it just was stuck in this small area, but when we are using RRT, the nodes have traveled to much further distances in the map. Let us add 100 more. Okay, so it is spreading even more. Okay, let's add 200 more. Okay, so after adding about 200 nodes, we have already reached our destination. Okay, and the path from the starting point to our destination is just shown like this. Okay, so as you can see that our work was done in a much using much less nodes as compared to random trees. I mean, our work wasn't even done after using 1,000 nodes, but here only after using like 421 nodes we are done. Okay, let us try for some other one. Okay, narrow passage. We'll just insert like 200 nodes. Okay, so in this case also, even in just 200 nodes, we have already found a path to our destination. So that is how good RRT is in exploring the map. Okay, we can use RRT to just explore many different part of the map. Suppose our destination was this part, just see it has already explored. So let us add more nodes. Let us add more. Let us add up to 1,000 nodes. Okay, but right here you can notice one thing. Even though I add more and more nodes, this path right here, it remains the same. I mean, it's not the shortest path, but it's not even updating it. Okay. Okay, so you can see after 1,000 nodes that it has explored the map in a very efficient manner. Okay. It has reached almost every point of the map within 1,000 nodes. So if we want to suppose explore any other part of the map, we can just find the path to that point. Just see, we have find another path. Okay, so now the only problem with RRT is that RRT only finds a path to your final destination, but it might not be the quickest or the shortest path. Okay, so to make RRT algorithm uh, able to find the shortest path, we need to like change the algorithm a little bit so that instead of just uh, you know uh, just branching out further and further, I mean it will branch out further, but we'll do something else instead of just connecting. Okay, okay, so now RRT star is just, I mean, an extension of RRT algorithm, and RRT star algorithm helps us to find the shortest path to our destination. Okay, so this is the previous region which we encountered using RRT. Okay. In this case, suppose if a node spawns over here. Okay. Now, if it was RRT algorithm, then this node is going to just connect to the nearest node. Okay. And it will just branch on. But in RRT star, we are going to change that thing. What we are going to do is we are going to introduce a what do you call search radius, and we are going to consider the nodes in this area, and we would find if we can like make a path which can like it can be shorter than the earlier one. Okay, so in this case we can see that this path right here, from this path right here, is shorter than this path. Okay, so instead of connecting this node to this node, it will just form this, it will just connect these nodes in this straight line and it will remove this. Okay, so just like this. Okay, so we have found an even shorter path to this point of the map. Earlier the shortest path which we found to this point of the map was this one. Okay, but after introducing the RRT star algorithm, this is the new shortest path. So that is basically how RRT star, I mean what we did differently in RRT star, so that we can find a better path as compared to RRT. Okay, so as we increase the number of nodes, okay, more and more nodes are going to just appear around the region, and then it will modify the path to a shorter and then even shorter path. So as progressively the node increases, so as the nodes increase progressively, so as the nodes increase progressively, the path will get shorter and shorter. Okay. So now let us take a look at RRT star, how RRT star works. Okay. So let us set our destination over here. Okay. Okay, so this is our starting point. This is our destination. Okay, let us add 10 nodes in the start. Okay, so this is how RRT star. I mean, it looks a bit different from RRT. As you can see in RRT, there were like branches spreading like this. But RRT star has more like straighter lines because it just updates the part to the shortest one. Okay, so let us add more and more nodes. So after adding about 110 nodes, this is what happens. So as you can see, okay, so this is, I mean, the paths are getting straighter and straighter as compared to RRT. Okay, in RRT there were many branches and sort because these nodes were just connecting to the neighboring one and then just creating a branch. But in this case, the branches are getting much straighter and shorter as compared to those. Okay, let us add more nodes. Okay, it is exploring the map. Okay, let us add 500 more. Okay, so but we still haven't reached our destination. Okay, so let's add more nodes. Let's add 200 more. Oh, we still haven't reached it. Okay. Okay, so as you can see, we have reached our destination over here, and it is quite a shorter path. Okay, you can let me show you. Okay, so you can see that it's almost like a shortest path. Okay, if we had used RRT, then there is a high chance of it like branching around these region and then coming over here like this. It will give us a much longer part. But because we change like how the nodes connect to each other, this will just like shorten the path after every node. So it will just give us almost what do you call almost the shortest part to almost every point of the map. Okay, let's add more nodes. Okay. Okay, let me show you something. Not only have we found the shortest distance to this part of the map, but if we move over to somewhere here, we we still have almost the shortest part to this part of the map also. Okay, even if we move over to this part of the map, still we have almost the shortest part to that part of the map from this point. So this is how RRT star can just connect thus, I mean, can find the shortest part to almost any point of the map as we increase the number of nodes. So if I add more nodes over here, it will probably fill this area also, and it will probably fill this area. And then after, I mean, it gets over 2,500 nodes or something, we will almost have a shortest distance to almost every single different part of the map. Okay, so that's how RRT star uses nodes to find the shortest path. Okay, so yeah, those are all the basic path planning algorithms. I mean, I just explained it briefly over here. I didn't go much into the code or anything, but I'll attach some for the because we don't have enough time now. Yogesh will continue his session soon, so I'll add more resources here about RRT and RRT star. But if you want to see Dijkstra's algorithm and its implementation, this is a really good video. Uh, this guy just explained it really well about how to implement Dijkstra's algorithm. Even if you don't have much knowledge about data structure and all, a good video about A-star algorithm is this one. Uh, this is the link to the demonstration. This demonstration you can try it later after the session. And this is a navigation playlist by MATLAB. It is worth watching. So do check it out. Okay. So I think okay, Yogesh would continue his session now. Okay. So thank you.
Hello guys. Can you just confirm that? Can you guys hear me?
Yeah, we can hear.
Okay, great.
Wait, I'll stop sharing.
Yes. So I hope now you can see the screen, right? Can someone confirm once? Hello.
Yeah, yeah, we can see. This time we can see.
Gopinath, can you see the PPT?
Yeah, yeah, I can see.
Okay, that's great. That's great.
Yeah.
Okay, guys. So Gopinath explained about different path planning algorithms and how effectively a mapping can be done. But the problem would be is availability of the map is not quite often. Like if the robot is exploring newer places, then the robot need to first build the map and then it need to proceed with all those path plannings and executions. So the SLAM algorithm basically helps the robot to create an effective path by analyzing the local surroundings of it. Okay. So basically, SLAM has two parts in it. It has localization and it has mapping. Okay. So localization refers to a process of estimating the pose. As we discussed earlier, pose is nothing but it's a position and the orientation of a robot or a system within its environment. So now if you see, for any terrestrial robot, there are three variables which define the state of the robot. Those are nothing but the x and y direction and the orientation of the robot. So with these three variables, one can easily define the state of the robot within its environment. So this localization basically helps us to estimate the pose of the robot with respect to environment. Okay. So basically these algorithms rely on sensor data, and through by processing the sensor data, it will be basically it will be matching and it will be like helping us in localization. Okay. Now speaking of mapping, so mapping is nothing but constructing a representation or the constructing a map of the surrounding and locating the obstacles, landmarks, and other features. Now, these maps can take various forms such as occupancy grid, feature-based representation, or topological maps. Okay. So based on our requirement, we will be choosing which map we want. And also, this mapping process requires a accurate localization information to ensure that the map has been accurately formed. Okay. So the thing is, like right now what it does is the robot will be keep on analyzing the surrounding, and it will keep on get the data of this environment, and then constructively it will build a map. But if in case the localization is not properly done, or if in case there is any error in the localization, then the map formation won't be quite accurate. So of course in reality there will be some errors in our system, right? That can be errors due to a sensor or error due to a physical bot or etc. So what we will do is we will be basically reducing those error, and we will be collecting the data through the sensors, and we will be constructing the map. So the thing is, Slam does both the things simultaneously. So that's what makes it much more unique and much more reliable. Okay, so it has a wide range of applications. This includes autonomous vehicles, service robot, drones, and even augmented reality. Okay, now let's see the mapping techniques in Slab. We have talked about three type of map, right? So this one is called occupancy grid. So occupancy grid basically it has basically it stores the value whether there is an object in that grid or not. Okay, so the black things which you see here are nothing but object, and gray I mean this image is not very exact. Generally these areas are unexplored areas. The robot haven't explored those parts, and white parts are places where the robot can freely move. That means there is no obstacles in it. So now talking about feature based mapping, so mostly these feature based maps are used in autonomous car auto self driving cars and all. So basically what it does is it will use lidars and also camera, and using those two things it will map those features, and it will represent the map according to the features. Now topological maps, mostly topological maps are used in drone system. Okay, so these type of this representation basically captures the spatial relationship between the different areas of the environment, which is like quite useful in case of drones. Okay, now let's talk about basics of Slum. So what are things required for Slum? So if you see robot perception, so firstly robot will be equipped with sensors such as lidar, sonar, and cameras. These are the general sensor which will be using to perceive its surrounding. So these sensor collects data about the environment such as distance, shape, and color, and some other things. So now data association. So now we have different data collected by different sensors. So now what we need to collect those data when we need to analyze those data, right? We need to bring in some relationship to integrate two or more data. Then only we can build an effective map. Okay. So basically this process involves matching the landmarks or matching the features basically. Now let's say we have lidars and cameras. So lidar will be giving us the distance between, or basically it will give a point cloud of the environment, and cameras will be giving us the images, whereas it doesn't contain the distance of it. Now while we integrate these two sensors, we can effectively get the object as well as its distance from the robot. So that's what makes the algorithm to build an effective map. Third thing called state estimation. So again, the state estimation somewhat comes in localization. So state estimate is nothing but it uses the algorithm to estimate the current position and orientation. Okay. So basically, position and orientation can be estimated by the uh, robotic model, kinematics and kinematic model, and also we can integrate sensors like IMUs, and we can also there is a sensor like their encoder, which will basically tells us how much the wheel has been rotated. So based on these sensor, we'll be getting different position, right? In an ideal case, all the position should be same because it's representing the state of the robot. So it should be same, right? But in reality, it won't be same. So we use algorithm to come up with a position which is like closer to the reality. And finally, we will be constructing the map. Now we know exactly where the robot is, and we have the data of the surroundings, data of the features, or like we have the data of our surrounding. Now what we will do is with those data, with those state estimation, we will be constructing the map. Okay, so this is what basically happens in SLAM. Now, speaking of state estimation, as I said, things won't be ideal, right? So there will be deviation from our case. Like, let's say the robot wants to move to 2,3, but then there might be some drift. The robot might end up in 2.5, 1.3, something like that. So we can't be very sure about where exactly our robot end up with. So we use these kinds of algorithm, these kind of filters to basically reduce the error of our system. We equip with we will be using multiple sensors. We'll be getting the estimated data from that. And see, every sensor has some sort of errors in it, right? Like, let's say IMU sensor might be might prone to error if you exposed to a magnetic field, or encoders will prone to error like when there is any drift in the robot. So what we'll do is we will be collecting those data and we will be formulating we will be guesstimating a current estimate of a robot to all this uh, various position, and this estimate that would be accurate to when we compare it with in a real case scenario. Okay, so commonly used filter would be Kalman filter. We will discuss about that in the later part of the session. So now challenges in SLAM. Now we have seen what is SLAM, where exactly we have been used, and what all things involved in SLAM. Now let's see what are the challenges in SLAM. Now, as I said before, if none of the sensors are 100% efficient, each and every sensor has its own errors, its own noises and inaccuracy in the readings. So those noises, if not rectified, can lead up to errors in the estimated post and also errors in the map. Second thing, data association. So these data should be correctly associated with the sensor reading. Let's say if the area is dynamic, let's say if the obstacle is moving, then we can't exactly say that we can't exactly formulate the map around it, right? Because the algorithm might think that it end up in a different place or in a cluttered environment where there are a lot of features in it. So like the data processing complexity will also be increasing. That's what our third point is. So SLAM algorithm can be computationally intensive because it is dealing with a large data set like image and also the point cloud. Again, it need to keep on get those images and keep on build up the map. So it is computationally complex. So again, but then like these algorithms are really helpful in building a proper map. So we can somewhat balance between the complexity and accuracy. And main thing, loop closure. Let's say if a robot let's say a robot is analyzing its surrounding. In one go it can't analyze each and every features in the surrounding, right? So it need to visit that place multiple times so that in a multiple orientation it need to sense the data, then only it can make a proper map out of it. Okay, so we need to ensure that the loop closure is there. Okay, now let's talk about the sensors you basically used in SLAM. So in general, in a most case, we'll be using cameras, lidars, and sonar. So camera will be giving us a visual information that can be used for detection, object detection, and tracking. We have seen that in CVI part, right? CVI session, right? So we'll be basically taking an image and we'll be detecting the objects around it and its motion. The thing is, the reason we are not only relying on cameras is cameras won't be telling us how far or near the object is. It will basically tell here is the object, here is this object, and this is like this much far apart, something like that it will be saying. So that's why we use lidars. So basically lidars is nothing but light detection and ranging. It will shoot a infrared rays, and it will calculate the time taken for it to bounce back, and based on the time the distance will be calculated. Okay. It will be using laser beams. So this will provide accurate 3D point cloud. That point cloud is nothing but it's a space. It's a spatial representation of the distance. Like it will tell us how far or near the object is. So lidars will be are useful in map construction. Now let's talk about sonar. Mostly lidars are pretty efficient than sonar, but where we use sonar is in a place where our laser beams cannot penetrate, like in case of water body. So in case of sea, then there'll be a case like the laser beam might get scattered or might not penetrate to the water. So in those places we'll be using sonar. So these will be emitting sound wave to detect object. It works very similar to lidar. Now, if you see, as I said, this is the cameras, and we are getting the features, and this is the lidar data. So we'll be combining these two data, and we'll be finding like, okay, there is a car over there, and this car is this much distance from the system. So those kinds of information we'll be getting through this thing. So these kinds of information are really important or really helpful in building a constructing a proper map around it. And this is the about the pure lidar data. We often rely on some other sensor fusions rather going with a one particular sensor, because multiple sensor are used to avoid the errors and also get a better efficient data. Okay. Now, yeah. Okay, we have seen like there are three sensors, and we have seen like not one sensor will give you an 100% accurate one. So we use multiple sensors. How will be using it? As I said, the camera will be giving you a 2D image, and the lidar will be giving some point cloud. How will you be integrating those things? So this sensor fusing algorithm basically helps us to combine two or more data, and it has some algorithm. I mean, it has some rules to follow. Certain mapping will be done, and based on that, this data will be combined. So SLAM basically uses variety of sensors like camera, lidar, and IMU. And by fusing these data, the robot can build more complete and accurate understanding of its surrounding. Now again, improving state estimate. As I said before, if we only rely upon one sensor, like let's say we are relying only on the state estimate, like system model, then we won't be able to like get the accurate thing, because the reality will be like bit deviating from the ideality. So in those cases, we use multiple sensors, and we will be getting a proper localization of our robot. As I said, only if you have a proper localization, we can build a proper correct map. Okay, and we will be overcoming sensor limitations. Now, let's say if in a place where, like, let's say if there is any drone which will be any vehicle which will be working on both terrestrial and aquatic. In terrestrial, lidars are efficient. In aquatic, the sonars are efficient. So basically, by sensor fusing, we are overcoming the limitations of each and every sensor. Okay. So for those things, we can use sensor fusing and probabilistic techniques. There are like few techniques which we'll be following for this fusions. Okay. So now if you see, a common thing in SLAM is Kalman filter. It's like, a very famous one, you can say. In most of the cases, we'll be using Kalman filters and some versions of Kalman filters, like extended Kalman filter based on our condition and environment. We'll be using some advanced version of Kalman filter. So basically, this Kalman filter works by two ways. It will predict and it will update. So firstly, it will predict the robot state based on the previous state and motion model. Let's say robot is in 2,1 and robot moves forward. Let's say in the y direction, it moves by 2 units. So it will be in 2,3, right? So that kind of, this is like a very basic ideation. So that kind of estimate will be first done. Second thing what it will do is the filter will incorporate new sensor measurements. Like it will incorporate the sensor measurements of IMU, sensor measurements of encoders, and some other sensor, some visual sensors we will be using. So it will be incorporating new sensor measurements, and it will be predicting the, I mean, it will basically, it will be taking all those data, and it will be like coming up with a like coming up with estimate which is like closer to it, closer to a reality condition, right? So basically this is how it works. The mathematics behind it is bit complex, but if you wish you can explore on it. Okay. So so basically in one so in if to summarize this, basically it will be guessing an position based on the robot's state and the model. Then it will be getting data from the sensor, and it will be updating the estimate, and then finally it will be like giving us an output. Okay. Particle filters will work somewhat like Kalman only, but then in particle filters, see, in Kalman filter, if you see, basically there is something called covariance and something called position, right? So basically, the position will be taken as a Gaussian bell. Like if you see, there is some. 1 second. Okay, I think most of you have seen this kind of bell, right? So this is something called Gaussian bell. So the amount of spreadness will be determined by the covariance, and this peak will be determined by the position. So basically, the Kalman filter will work in this way. It will be assuming it as a Gaussian blur. It will take a probabilistic approach. Whereas in case of particle filter, it will be discreting the position as set of particles. Okay, each representing a possible state. Then it will wait and resample based on the likelihood of being correct. Like let's say if some 10 particles are together and one particle is some far apart from it, so then there is a case like that one particle might be an error, right? So something like that, some conditions will be applied, and those kinds of low weighted particles are discarded. So this way we can reduce the error, and we can construct some efficient map. Okay. Again, now let's talk more about map. Okay, now we have seen like how to you know how to overcome those errors we have seen, and we have seen how SLAMP works. Now we need to create a map around it. We have the features, we have the um, data of the surrounding. Now we need to construct a map. So basically there are two kinds of map. One called binary map, binary occupancy map, and second called probabilistic occupancy map. So what we will be saying is, if there is any object, that grid will be marked as 1. If there is no, if it is free, then the grid will be marked as 0. Okay. So by that way, if you see here, the black ones are marked as 1 and the white ones are marked as 0. So white one signifies that there is no obstacle in the pathway, and the robot can freely move in that part. But the black one represents there is some obstacle in the pathway, so it can't move. Now there is also called gray area, right? Area is nothing but it didn't explore that part. Like it doesn't know whether it is free to move or it has an obstacle in it. So the task of a robot is to explore all the gray area, so that it will be like determining whether that area is free or that area is occupied by an object. Okay. So we will see more into this technique. Okay. So now let's talk about approaches in SLAM. So basically there are two based approach. One is graph based approach. Second is odometry based approach. This odometry based approach is something which we have discussed before, right? Like it will be taking the pose, and based on the pose it will correct the pose, and it will map the surrounding to it. Okay. This is something called odometry based approach. So it has two things. it will be incrementally mapping. Like it will be visiting the place and again, and it will be like mapping the surroundings to it. And again, it's prone to drift errors. As I said, the reality won't be same as ideality. So in reality, there will be some drift. Again, you need to integrate some sensors and you need to integrate some algorithms. So like to reduce that drift. Speaking of graph based approach, so what we'll be doing is we'll be collecting the data. We'll be collecting the data again and again. Then we will plot it. Then we will like then we will like correct the position. Okay. So that one common method is called iterative close point approach. So it's very simple. I mean, what it does is it, let's say it followed a loop path. So based on the loop path, there is some output which it got, and again it will follow the path again and again. So like it will be getting different up. I mean, in each and every loop, it will be getting one data, right? Now what it does is it will club those data and it will find the closest point between them, because it's assumed that that point is what deviated in the next iteration. So what it does is it will minimize the distance between them, sort of like an average, not exactly like an average, but somewhat like that. So what it does is in the end, when there are multiple loops, when it been measured multiple times, you'll get an map which is like quite accurate to the surrounding. And again, these algorithms are used to construct a map by aligning the point clouds, something somewhat like this, you can say. Okay. Now comes optimization. Again, as I said, reality is different from the ideality. So now in reality, there will be drift. So what we will do is basically we will be using algorithms like there is one like this kind of optimization. So what it basically does is it will be following a loop. Okay, the robot will be following a loop, and in the ideal condition of the robot will exactly cover the loop, but in a real condition the robot will not exactly cover the loop, right? There will be some sort of final drift. So that those 2 points will be clubbed together, and again, based on those 2 points, other points will also be connected, and other points will also be, uh, shifted, so that these 2 points are clubbing together. So based on that, once we form a closed loop, then the data are compared to, to create a map. This might sound bit complex or something. There is a video explanation. If you see here, this should be the ideal map, right? But in the case of measurement, the map is somewhat like this. We know for sure this is not the real map, and also this is the position. This is the position of the. This is the real position of the robot at particular timestamp. Okay. So in ideality, these 2 points are same. All right. Because these 2 points are measuring, giving out same data. But what happened is, I mean, but in reality, there will be some drift, right? So what it does is, okay, if you can see, initially it was far apart. Now what happened is these two positions are overlapped. So which the entire data is also a bit structured. Previously it was like very random one. Now it is like a bit accurate compared to the last time. So this is how this optimization will be resulting in some good amount of map, the good map. Okay, iteratively, if you do this, then you will get more and more. a map which is like closer to the actuality, right? So these are the algorithms we'll be using, and we'll be building a map. So once we build a map, then we are free to do any sort of path planning we want and any sort of execution, right? So basically, this is all about SLAM. A SLAM will do two things: localize. It will localize its position, and it will map the surrounding based on the sensor data. Now, the idea lies in like how effectively it does. That's where we use multiple different types of algorithms to it, right? So this is like a brief overview of SLAM. I hope you guys understood, like at least you guys got a good idea on SLAM, right? If you guys have any doubt, you can ask. Then next case we'll see the implementation of it. You'll see how visually it will work. If you guys have any doubt, you can ask. Okay, so I assume there is no doubt. I mean, no problem. I will share you this PPT, so like you can go through again, and also you can ask the doubts in the end of the session also. Okay. Now let's see the implementation of this SLAM. Okay. So now we have seen these algorithms. We have seen like we'll be running the robots, and somehow we'll be getting the data of our environment. Let's see how practically we can see this. Okay. I think now this would be a bit interactive because we'll be literally we'll be visualizing like how exactly it works, right? So first thing, I assume that everyone have Gazebo in their virtual machine. If in case you are trying it, everyone have already installed Gazebo, right? Can someone confirm once? Hello. Okay, fine. So no, not an issue. So basically, what we are going to do is, so basically, there will be a map, a pre-built map in Gazebo. So we will be running the robot in that map, and we will be getting the LiDAR data from it. Based on the LiDAR data, we will be constructing a map. So that's what we're gonna do in this simulation part. So for that, first we need to install TurtleSim simulation, TurtleBot 3 simulation. So for that, sudo so we are using ROS Humble. Okay, so we need to install this package. But the thing is, I have already done this, so it might be a bit fast for me. If you're doing it for the first time, you need to do it. Will take some time. It takes some time to install each and every packages. Okay. So after this, we'll be also installing messages package. Again, it's already been done in my case. So what we're gonna do is first let's visualize the map first. Okay. Just a second. Okay. First, let's launch the Gazebo file. If you see on tab, I get these things, right? Now in this Gazebo folder, so now we will be launching the map. So if you see, these are the packages available. So we will be launching world. Okay. Sorry. Okay, guys. So if you see, this is our robot, and this is the environment around it. Now, if you see this these black color are nothing but these are walls, and also this green color is nothing but it's a boundary. Okay. And these cylindrical gray things are nothing but it's an obstacles around it. So this is our bot, and this is the lidar, you know uh, lidar rays, you can say. So whenever it is dark, which it means that it hits the surrounding and it reflects back the, it hits the surrounding and the waves are getting reflect back. Okay. So in these places we can easily get the data. But in case of the gray part in these lighter areas, which means like it's not hitting any target. Okay. So we will be we will be moving this bot and we will be constructing a map around it. That's our task. Okay. So for this, in order to move the map, we are going to use teleop keys. We are going to use teleop test keyboard. Okay. Yes. So if you see carefully, you can see I can move the map, right? I can move the bot around it. It's like literally I can play with it. Just a second. Yeah. Hmm. Uh, I hope my screen is visible, right? Can someone confirm once? Is my screen visible?
Yeah, it's visible.
Hello? Okay, okay, good. So if you see the part over here, this is the nothing but data due to the camera. So in Turtlebot, there is basically camera and lidar installed. So this is nothing but a camera data. If you see, the camera is detecting this object and also these cylinders, right? Now if I move this camera, just a second. Sorry. Yeah, if I move this camera, this image is changing. Okay. Okay. So what we're going to do is we're going to keep on construct a map around it. Okay. So for that, let's open RViz too. So RViz is nothing but it's a tool which used to visualize the surrounding, visualize things. Okay. So what we need to do is we need to visualize a map in it, right? So basically, what a robot does is the robot will be like publishing the lidar data, and we need to use that lidar data and we need to construct a map around it. So before that, before that, let's see what are the topics there in this. Okay, let's take ROS 2. Now these are the topic it's present in this robot. So basically these topics basically deals with the data, the camera data of it. Now these will be raw, compressed, depth data, and stereo data it has. Then it has clock in it. It has command well. So this command well is something which is used to move the bot. Now, basically, the robot will be subscribing the data from the command well, and based on the data, it will be moving. So whatever the teleop thing which we are using here, basically what it does is it will take the input from the keyboard and it will publish the data to this command well node. Got it? So this is nothing but IMU. As I said, we also have IMU sensor in the turtle sim case. Okay. So again, all those algorithms will be running in behind, so we need not worry about it. But in real case, we need to implement everything manually. Similarly, we have odometry data, we have a robot description, we have a TF, and we have scan. So this scan is nothing but this scan is what it will be publishing the data of the lidar. So we will be taking this data along with the other data and we will be formulating the graph. Got it? So let us keep this aside. Okay. So now what we need to do, first we need to visualize the map. So we will go and we will add the map to it. First, let's add robot model. I mean, this is not necessary, because anyway we won't be like visualizing the robot. If we want, we can have it. So now let's search for map. Yeah, so we have map, right? So now we are adding map, and we are also adding odometry to it. Yeah, odometry is here. I mean, you can add anything you want. You can add all these datas. You can add if you want to visualize the depth cloud, you can add this. If you want to visualize the camera, you can add this. And also, if you want to, I mean, there are a lot of functionalities here. But let's for now only focus on map and odometry. Okay. Now what I'm going to do is, okay, I have created a map, but now I need a topic for it to subscribe, right? Sorry, publish, right? So what I'm going to do is, just a second. Uh, just a second, guys. Hmm. Okay, just a second. Okay. Yeah, okay. So what we're gonna do is we're gonna launch this file. because this file is what will be, launching the map. So mapping launch.py. Okay. So it's very clear that all the cartographic data are being present now. Now we can now we will see and visualize it in ArcGIS. Yeah. So if you see now, there is a map over here. You can clearly see this is what the robot has been visualized. Right. We will also add odometry to it. Yes. Hmm. So if you see carefully, this is where our robot is, and also yeah, if you see here, this is where my robot is, and this is the map it's visualizing. Okay. So now what I will do is I will move this map. So like I'll move this robot. Okay. Yes. Hmm. Yeah. So I need to move this map unless the entire map has been until the entire map is formed. Now, if you see, as is explore new places, slowly this gray area has been turned into black, in black and white, right? So black actually means there is some obstacle, which in case it's cylinder and walls, and white is nothing but it's like nothing but free space. So now my task is to explore all these places. See, for the simulation case, I am showing you I'm manually doing it, but we need not do this manually. Again, we have a lot of algorithms to automate this process. So basically this process capture all the features around it. Okay, which is useful in forming a good map. So if you see, as the robot progress, the map is keep on getting updated, right? I think you can see it clearly. Hmm. So now how we need to focus is, just a second. So as the robot progresses, we get clearer and clearer image. So now if you see, this is the proper map, I would say. So this is what we wanted. So now what we need to do is, now we formed a map. This is the surrounding. This is the surrounding, and we scan that surrounding and we formed a map in our ArcGIS. Right. Now we need to export this map. That's it. Our job is done. So, see, in ideal case, it'd be very easier. In a real case, you need to encounter a lot of errors. But let's see, this is how it works, and we also got the map out of it. Okay. So now what we will do is, now we have the map in ArcGIS, right? So now we need to export it into image. Then only we can use the binary. I mean, we can use the threshold. We can make it into a pixels, and then we can implement the algorithms which Gopinath taught us, right? So for that, what we will do is we will use a module called nav2. And guys, the issue is, I don't know whether you guys have follow till now, but if in case you want to do this, if you want to do the further step, you need to install these many packages first. So if you want to install these packages, it takes a lot of time. So Anyway, I'll just share all the data with you. You can do it freely. You can get do it slowly and you can understand. For now, I'll just show. I installed everything previously, so I'll just show you the direct command. So now what we're gonna do is, first we need to go to the destination folder, right? Where I need the map, my map to be. So I need my map to be inside my workspace, inside the source, and inside my package, which is nothing but navigation underscore ss. This is the file which I have zipped it and which I have sent you guys. So what you need to do is you need to unzip it and you need to upload it. I mean, you need to copy paste it in source file. Then you need to go. Then you need to do concat build, because it's like you're building a package, right? Then config. So I want my map to be here, because if in case I want to use my map in any further case, I will be taking the map from there and then I will be using it. Okay. Now let's, yeah, we'll just have it inside. So now the command is, so we will be using nav2 map server. So this map server basically will be converting that map into an image. I'm saying it need to convert into map saver. It need to save the map and CLI, and the file name should be file name. Let it be turtlebot 3 summer school. Okay, map name can be anything, right? Now, oh, sorry, 1 second. Hmm. Sorry. So I need to do map save as server. Yes. So if you see here, previously there is so if you see there is an image. Oh, sorry. If you see in this config, can you see the map here? Can you all see the image? So this is nothing but a map which we got from our LiDAR data. So we can use this map and we can construct like whatever we, first we'll be doing CVA, and we'll be like getting the map, we'll be converting that into a binary matrix. Then that binary matrix will be used to, implement those algorithms. You can also see this map may not be that efficient because I haven't run it multiple times. I only run it once because I'm manually controlling it. So you can automate this process and you can ensure that you're constructing a proper map. Okay. So these are the things which you can do using the SLAM. So this is how basically the SLAM works. You will do it in a real case. See, now the map and all, map which is in Gazebo and all, so this is nothing but a virtual environment. I couldn't able to implement it in practical. That's why I'm using a virtual environment and I'm simulating it. In a real case, you can implement it in the workspace where you are, where the robot is working on, and that the area of that workspace can be determined using this process. Okay. So now we have an image. It's our time to process it and do all those controlling. So that's all about SLAM. So I hope you guys got an understanding of what is SLAM, where it's been used, and how all we can use it. And also we have seen a small implementation of SLAM. Once we get a map, we can do whatever we want. We can again use that map for navigation, and all those things can be done, right? So now officially we are at the end of the session. So I hope you guys got a clear understanding of what we thought here. So though this might be a bit complex to understand in a one go, if you guys are interested in it, you can definitely explore these topics, because there's like a countless amount of amount of topics and there are a lot of things to learn. Okay, even we after doing this many research are not that well versed in these topics. So if you guys are interested, there are a lot of documentation available in internet. There are a lot of YouTube videos to follow. So feel free to, even reach us if you guys need any resources or something. Now, if you guys have any doubt, you can ask. Uh,
One of the guys had a doubt actually.
okay. Oh, okay. In chat.
Yeah,
Sorry. What is the doubt?
yeah. Let me clear it. I'll share my screen.
Okay. Okay. Fine.
Yeah, you can see my screen, right?
Yeah. Yeah. I can see. Yes.
Yeah, okay. Okay, so your doubt was that what is exploration bias and what is goal radius. So goal radius is basically the size of this goal. So if I just increase the goal radius, then the circle will get bigger and bigger. Okay, so more number of nodes will be detected if the bigger the goal radius, the more nodes will be detected. And exploration bias is suppose I put exploration bias to, let us say, yeah, let us say about this. So what happens is that if I insert a node, if I insert some nodes, then they will move towards the goal with this much percent of probability. They will move towards the goal with a probability of 0.45, and the rest of the time it will just randomly spawn any node. So you can see that in this case, when I increase the exploration bias, then all the nodes were more towards the goal. And initially when I started, I just placed it on 0 because then it just spawned random nodes. But if you want your nodes to like move towards the destination, then you can increase the exploration bias, and that will just help you get a route directly towards your destination. So yeah, that's it. That's basically it. Yeah, I hope you understand.
Any other doubts? Okay, guys. So we came to the end of summer school. I hope you guys learned a lot. I can clearly understand that these sessions might be a bit heavy for you guys because you guys exploring these topics for the first time. So don't worry. Just you guys will get the recordings. You guys will get the assignments. Explore on these topics if you guys are really interested in. And trust me, these topics are really exciting. No. Once you implement it, you will get to understand it much more clearer. If no one have any doubt, I think you guys can leave. The session has been ended. If you guys have any doubt, you can stay back and you can ask. Thank you guys. Thank you for attending.